Hey, hello students, how are you all? Well, I'm hoping that you all are doing great. You all must be fit and fine. Well, guys, I'm sure that you all are also looking forward to prepare for your boards examination as well as the most important competitive examinations such as JEE and NEET. And when you really look forward to prepare for this kind of examination in the best possible way, where else you can go other than Physics Wallah? So guys, this is Sagar Darvi, your chemistry teacher, and I welcome you to Batch of Excellence at Physics Wallah. So as you all can see on your screen, we will be discussing important part of chemistry, which is an organic chemistry. And to begin with, in this Batch of Excellence, where we will be covering your board syllabus, along with which JEE and NEET as well. And to begin with, we'll be starting the first important chapter, which is Haloalkanes and Haloarenes. Well, I'm sure that you guys have gone through the syllabus. You must have seen your textbooks. So you must have come across some part of this chapter, Haloalkanes and Haloarenes, which includes some important reaction mechanisms. Yes, dear students. And that's why in this chapter, before entering into the reaction part, we will be first discussing about the reaction mechanism. So guys, to begin with, let me show you what exactly are we going to learn in this chapter. So here is what we are willing to cover in our today's class. Today we'll be discussing about the introduction of reaction mechanism, followed by the important reagents such as electrophiles and nucleophile. We'll brief them first. Followed by we'll be talking about some important solvents and the interaction of these reagents with the solvents. Followed by another important term that we must understand in order to understand the reaction mechanism, which is leaving group. Sometimes it is also called as nucleophile. And followed by, we'll be starting with actual reaction mechanism. Today, we'll try to cover the unimolecular nucleophilic substitution reactions. So guys, to begin, let us first understand the name of this chapter, Haloalkanes and Haloarenes. What does this name exactly means? Well, guys, when you look at this term, haloalkanes and haloarenes, one thing is for sure, what I can understand from here is that these compounds are made up of alkanes and aromatic compounds. Now, if you see the initial part of this term, haloalkanes, this clearly indicates this must be a compound of an alkane containing halogen atom. And haloarenes, meaning this must be a compound of aromatic hydrocarbon containing halogen atom in it. And hence, in general, we can say haloalkanes and haloarenes are the derivative of alkanes and aromatic hydrocarbon in which one or more hydrogen atom we substitute with the respective number of halogen atoms. Now, whatever I have said, to understand that in a better manner, let us have a look at a simple reaction which explains this in a simple possible way. Well, you can see we have got an ethane. Imagine if I'm carrying out some reaction where one hydrogen atom of ethane we are substituting by a chlorine atom. So I will be getting a product which I'll call it as chloroethane. So it's a derivative of an ethane in which one hydrogen atom is substituted by halogen atom. And one very important feature that I want you guys to have a look at is the halogen atom is connected to sp3 hybridized carbon atom, of course because your parent compound was an alkane. Hence we say haloalkanes are halogen derivatives of an alkane obtained by replacing one or more number of hydrogen atom with the equal number of halogen atom. In a similar manner, if I take benzene as my parent and if I substitute one of the hydrogen atom of benzene with a halogen atom, I will be getting a product which I'll call it as halobenzene. Now the difference between the haloalkane and haloarene is that in case of haloalkanes, the halogen atom is connected to sp3 hybridized carbon atom, whereas in haloarenes, the halogen atom is connected to sp2 hybridized carbon atom. So guys, this is how we simply get haloalkanes on haloarenes by the simple substitution reaction from a parent compound such as alkane or aromatic hydrocarbon such as benzene molecule. Well, now that we have got introduced to what are haloalkanes and haloarenes, let us talk about the characteristics reactions of these compounds? Well, so when you talk about, let's say, haloalkanes at the moment, haloalkanes are the compound in which halogen atom is connected to sp3 hybridized carbon atom. Such kind of compounds are found to be showing two of its important characteristics reaction when they are allowed to react with an electron rich species. Well, now I use term something called as electron rich species, which means before understanding the reaction, we need to also understand what are those electron rich species. But let us assume that we know something called as electron rich exists. So in presence of electron rich species, which is could be a nucleophilic or could be a basic in nature, this haloalkane shows two type of its important characteristics reactions, which are called as nucleophilic substitution reaction, which we abbreviate it as SN reaction, or depending upon the nature of that electron rich species, it may show the elimination type of reaction. To understand this in even better manner, let us take an example. Well guys, so you can see we have got here some alkyl halide, that is haloalkane, and I'm allowing this compound to react with some electron rich species. So depending upon the nature, that electron rich species could be basic in nature or could be nucleophilic in nature. Well, we are going to discuss about this little later, but just to give you a basic information of it, if any electron rich species which has a tendency to attack at electron deficient center such as carbon, then such electron deficient species we call it as nucleophile. I repeat, any electron rich species which has a tendency to attack at electron deficient center, which is carbon, then that electron rich species we call it as nucleophile. On the other hand, if an electron rich species has a tendency to attack at electron deficient atoms such as hydrogen, meaning if the same electron rich species is going to attack at H plus instead of deficient carbon atom, then dear students, that electron rich species we would be calling it as a base. So let us assume I have got some alkyl halide and that electron rich species is base. So by definition, base is the substance which has a tendency of accepting the proton. So let's say base attack at the deficient hydrogen atom, meaning this H is lost in the form of H plus. So the sigma bond will shift further and the X as a leaving group will leave from here. What do we understand from this? From a given substrate, hydrogen and halogen have been eliminated. A process where atoms have been eliminated or a group of atoms have been eliminated, such reaction we refer them as the elimination reaction, and such elimination reaction results in the formation of alkene as our product. So if an electron rich species is basic in nature, then our alkyl halide is capable of showing one of its characteristics reaction called as elimination. Now let us consider example of electron rich species which is going to behave like a nucleophile. So let's say I've got some nucleophile. So what are nucleophiles? By definition, they have a tendency to attack at the deficient center. So let us assume the earlier thing which we have shown is not happening. Okay, let's consider your substrate is still intact and the nucleophile is allowed to react with the substrate, and the nucleophile is attacking at the deficient carbon with the simultaneous loss of X in the form of X minus. So if you see the product, the only change that you see is halogen atom seems to be substituted by a nucleophile. Since a reaction is such where one of the atom or a group of atom is substituted by another atom or a group of atom, such reaction we refer them as nucleophilic substitution reaction. So what do we understand from these two reaction is alkyl halide is capable of showing two of its characteristics reaction depending upon what is it exposed to. If it is exposed to a base, then they will show characteristics reaction which is an elimination reaction, and if they are exposed to nucleophile, then they will show their characteristics reaction of a nucleophilic substitution reaction. Now my dear students, to understand these reactions in detail, before we enter into the actual reaction part of haloalkanes and haloarenes, we all need to understand reaction mechanisms of this reaction, and hence we are first entering into the reaction mechanism part of alkyl halides. So guys, let us first begin with the reaction mechanism. Well, in this you can say a subtopic of alkyl halide, that is reaction mechanism, we will be learning some important mechanism. Just to name them, we'll be talking about under nucleophilic substitution, we'll be discussing bimolecular nucleophilic substitution reaction, written as SN2. We will also be discussing unimolecular nucleophilic substitution reaction, which is SN1. We will also be talking an important reaction mechanism. Well, if you just go back and see previous year question paper of JEE Advanced, you will find the question have also been asked from this part, that is neighboring group participation, called as NGP. Well, other than this, there exists another type of mechanism which comes under nucleophilic substitution. We call it as SNI. Probably we'll be discussing that in the chapter of alcohol, so we are not covering it here. Other than nucleophilic substitution, as we mentioned, we'll also be talking about another characteristics reaction of alkyl halide, which is elimination. And under this elimination reaction, we will be discussing bimolecular elimination reaction, abbreviated as E2. Then we'll be also talking about unimolecular elimination reaction, which is even, and followed by unimolecular elimination via conjugate base, which is more often called as E1CB. Well guys, this is what is the scope of reaction mechanism chapter. Once this is done, then we'll be entering into the preparation and chemical reactions of alkyl halide. So to begin with, let us learn first about the nucleophilic substitution, in which, as we saw in the beginning, our today's learning objective includes learning unimolecular nucleophilic substitution reaction. But like I said, before you learn the reaction mechanism, you need to understand the term called as nucleophile. Hence, it is important for us to learn the reagents in detail first. Well guys, what exactly are the reagents is the part of GOC that we learn. But just to brief you, let's say if I have to represent any reaction. So the simple way of representing reaction is what? Reactants getting converted to product. So when you talk about reactants, well, reactant generally we classify into two types. One is a substrate, another is reagent. When these two interact and results in the formation of desired outcome, you call it as product. So this is how we generally represent a reaction. You can see the reactants are of two types. One is substrate, other is reagent. So what is reagent? Reagent is that reactant which has a tendency to attack on a substrate. So the one who attacks is the reagent, and the one who undergoes attack from a reagent is what you call it as substrate. And as a result of interaction between these two, if you get the desired outcome of that reaction, then that desired outcome is what we call it as a product. Hence everyone, I would say reagent is that species which has a tendency to attack on a substrate, and that species who attacks, that is reagent, further could be of two types, which is what we call it as electrophilic reagent or nucleophilic reagent. Let us try and understand these two terms first. Well, again these terms are self-explanatory. If you look at this term electrophilic reagent, the term electro represents electrons, philic meaning loving. So any reagent which is electron loving would be referred as electrophilic reagent. Now think logically. If any species has a tendency to love electron or electron rich center, meaning that species itself must be electron deficient. And because it is electron deficient, it has a tendency to love or attack the electron rich species. Hence, when we define electrophiles or electrophilic reagent, we say electrophiles are electron, this is important, electrophiles are themselves electron deficient species which has a tendency to attack at electron rich species or electron rich center, you can say. Alright everyone? Whereas the second term is nucleophile or nucleophilic reagent. Again, if you see the term nucleophilic, the first part of the term nucleo correspond to nucleus and the term philic correspond to loving. So from this term, anything that loves nucleus is nucleus loving, that is nucleophilic. We all know the fact nucleus contains protons and neutrons. Neutrons are chargeless, whereas protons carries positive charge. So anything which is loving the positively charged species, positive charged species generally are found to be electron deficient, because in nucleus there are never electrons, right? So you can say nucleus is kind of positively charged species, meaning it is electron deficient species or a center. And if anything who is going to love that nucleus, meaning that species itself must be electron rich and hence has a tendency to attack at that electron deficient center. Hence everyone, we say nucleophiles are themselves electron rich, but they have a tendency to attack at electron deficient species or electron deficient center. So simply when you talk about nucleophile, we generally symbolize it like this. Nucleophiles are symbolized as Nu electron pair. Sometimes it is also symbolized by putting negative charge on that, because it could be lone pair carrying neutral species or could be negatively charged species as well. When we talk about electrophile, we simply represent them as E+. Now, the best way probably you all can remember is nucleophile, right everyone? So from this first alphabet N, you can remember anything which is negatively charged, N for negative charge. So negatively charged species will be called as nucleophile. So logically, nucleophile which themselves are negatively charged will have a tendency to attack at the deficient center, which sometimes, or you can say generally, they are positively charged species. So just to conclude, nucleophiles are electron rich species, because N meaning negative charge you get because of electrons. So they themselves are electron rich species and has a tendency to attack at electron deficient center. And on the other side, electrophiles, of course they are going to be themselves electron deficient, but has a tendency to attack at electron rich species. Now dear student, let us understand in detail how do we exactly classify these electrophiles and nucleophiles. Hence the next part that we want to learn is the classification or the types of electrophiles and nucleophiles. Well, let us first talk about types of electrophiles. So what we are looking forward here is about electrophiles. Okay, so we classify electrophiles into two categories, cationic and neutral. As the name suggests, if the deficiency of electron on a particular atom is characterized by the presence of positive charge, we call it as cationic electrophile. I repeat, if the deficiency of electrons on a particular atom is characterized by the presence of positive charge, we call them as cationic electrophile. So you can see here, NO2 plus nitronium ion, NO plus nitrosonium ion, CH3 plus, that is methyl carbocation, chloronium ion or bromonium ion, etc. All are the species where they are carrying positive charge. So the deficiency on that particular atom is characterized by the positive charge. Hence we call them as cationic electrophiles. Okay. Second type of electrophile, we call them as neutral. So if you look at BF3, well, structurally if I write it this way, BF3, that's how we represent BF3. Well guys, tell me from the basic that you guys have learned earlier, if I ask you what is the hybridized state of boron, you would end up saying boron, since having 3 sigma bond, its hybridized state is sp2, right everyone? So if this boron is in sp2 hybridized state, that clearly indicates out of 3 p orbital, only 2 of the p have been used in the hybridization of this boron. There's one more p which seems to be vacant. So due to presence of this vacant p orbital, this boron can always accept electron, or you can say this boron can always invite attack from electron rich species which is nucleophilic. So if any species which invites attack from the nucleophile themselves has to be what? Electron deficient. Hence, such a species in which boron is not carrying any charge but yet electron deficient belongs to a category of a neutral electrophile. Another way of looking at it is you can see boron is having 3 sigma bond. That clearly indicate has got only 6 electrons in its valence shell, which makes it electron deficient. That is just another way to look at it. So such species which does not carry any charge on it but yet electron deficient belongs to a category of the neutral electrophile. Hence molecules such as BF3, AlCl3, ZnCl2, SO3, such species has a central atom which is deficient but yet not carrying any charge on that. Hence we call them as electrophile but neutral. Alright everyone. Now let's have a look at the nucleophiles. Like we have categorized electrophiles here, we also categorize the nucleophiles. Alright everyone, just hold on. It's just that nucleophiles we classify into 4 categories. Just like cation, if you look at this, OH minus, NH2 minus, hydroxide, amide, methyl carbanion or chloride ion. See, whenever you see any species carrying negative charge on that, that clearly indicates that atom is electron rich. And the magnitude of charge tells you it is electron rich with how many electrons. Like, if I say I've got OH minus, that indicates this oxygen has 1 extra electron. Hence the charge on oxygen is -1. So presence of negative charge always indicate that particular atom is electron rich. And if it is electron rich, by definition, it is nucleophilic in nature. Hence, the first category of a nucleophile, we call it as anionic nucleophile. And these are several examples. Of course, you can add many to the list. You can add PHO minus, that is phenytoin. You can add carboxylate RCO minus, so many of them. Right, everyone? Well, other than anionic, look at several examples. Like we have got water, where oxygen carrying 2 lone pair. We have got ammonia, nitrogen carrying 1 lone pair. Alcohol with oxygen carrying 2 lone pair. Ether carrying electron rich oxygen. Primary amine where nitrogen carrying 1 lone pair. Of course, you can have many other than this. All these species are such that they are not carrying any charge on it, like anionic nucleophile. But due to presence of heteroatoms such as oxygen and nitrogen, which is carrying at least 1 lone pair, makes it electron rich. Such molecule where at least 1 atom carries lone pair, as a result of which they becomes electron rich and hence has a tendency to attack at electron deficient center, we call it as neutral nucleophile. So after anionic, we have got neutral nucleophile. Then there comes 2 more important categories. The third one is pi bonded nucleophile. Well guys, this reminds me of one of the reaction. As we will progress in organic chemistry further, you will come across several reactions such as acid catalyzed hydration, then you will see oxymercuration, demercuration, so on and so forth, where you will see compounds such as alkene will be allowed to react with electron deficient species. So when you have got an alkene which is allowed to react with electron deficient species, then this pi bond of alkene attacks at the electrophile. Then this pi bond of alkene attacks at electrophile. Now just revisit the definition of nucleophile. We say nucleophiles are electron rich species which has a tendency to attack at electron deficient center. You call it as nucleophile. Now this pi bonded species attacking at the electrophile, which means certainly this is electron rich, but the richness of electron is not characterized by negative charge nor by a lone pair. It is characterized by the presence of pi bond. Hence such species which are carrying pi bond, we know the fact from chemical bonding, it is a loosely held electron cloud. So because this electron cloud is loosely held, it will always have a tendency to attack at the deficient center. Hence such type of nucleophile where the richness of electron is expressed by a pi bond, belongs to a category of pi bonded nucleophile. So just like alkene, we have got alkyne or even benzene. Well, who will forget the characteristics reaction of benzene? That is EAS, electrophilic aromatic substitution reaction, which is a characteristics reaction of benzene. That reaction also is triggered because benzene acts like a nucleophile. So that's your category number 3. Now we talk about the fourth one called as ambident or ambidentate nucleophile. Well everyone, the first example that you have got is cyanide ion. Alright, that is cyanide or nitrile ion. And the second one is nitrite ion, nitrile and nitrite. Okay, now what is ambident? Well guys, if you look at this structure carefully, this anion is such where the electron richness is at carbon. You can see this carbon is anionic, so it is electron rich. Also, nitrogen is also electron rich. So cyanide is such electron rich species where the nucleophilicity is residing on both the atom, carbon as well as nitrogen. What is nucleophilicity? Tendency of an atom to donate electron pair is nucleophilicity, and the atom which carries that lone pair is a nucleophilic site, SITE. So in this molecule I can see clearly there are two nucleophilic sites. One is carbon, other is nitrogen. Although such species has two nucleophilic sites, when such species will actually enter into reaction, you will see this molecule will use any one of the two nucleophilic sites, either carbon or nitrogen. Such a molecule having two nucleophilic sites, but during the course of reaction uses any one of the two nucleophilic sites or a center, we call them as ambident nucleophile. Well, the same thing we also learn in the coordination chemistry, right everyone? But instead of nucleophile, we just use a term as a ligands, ambidentate ligands. Well, over here, I'll call a nucleophiles having two nucleophilic sites, but during the course of reaction which uses any one of the two nucleophilic sites belongs to a category of ambident nucleophile. Same is the case with the nitride. If you see these two oxygens, ideally negative charge in conjugation with the pi bond, which is the condition for resonance. So if I draw another resonating structure, the negative charge will delocalize and the pi bond will go on oxygen. So now anionic oxygen in another resonating structure will become doubly bonded O, just like this. And the doubly bonded O upon delocalization of a pi bond will become anionic oxygen, just like this. What does that mean? These two oxygens are ideally equivalent. Hence, I am considering any one of that. So, if you look at the nucleophilic site, as of now in this resonating structure, this is the anionic oxygen. So, this is one nucleophilic site. This is equivalent of this, so I am not considering this simultaneously with this. So, another nucleophilic site is nitrogen atom. Yet again, just like nitrile, even nitrite is such an anion having two nucleophilic sites. But during course of the reaction, it is going to use any one of the two, and hence it belongs to a category of ambident nucleophile. So guys, one simple thing I want you all to focus on is your electrophiles are of two types, cationic and neutral. Nucleophiles are of four types, anionic, neutral, where heteroatom carrying at least one lone pair, pi bonded such as unsaturated hydrocarbons, and ambident, where you will be having two nucleophilic sites, but during the course of reaction it will be using any one of the two nucleophilic sites. You call it as ambident nucleophile. Now one important thing I want you all also to learn is, if you see ever any electron rich species that is anionic, so all anionic species will always be nucleophilic, because presence of negative charge will certainly indicate that there is one or more extra electron present, which makes it electron rich. But presence of positive charge need not always makes it electrophilic. Presence of positive charge need not always makes it electrophilic. For example, if I talk about ammonium ion, alright, let's say if I'm talking about ammonium ion, NH4 plus. Structurally, if I represent it, it will look like this. N carrying 4 bonds. And if you find out the formal charge on nitrogen according to the Lewis structure, you'll have a positive charge here. So at first glance, we feel that even this molecule should belong to a category of a cationic electrophile. However, let me tell you, electrophiles conceptually are the ones which are electron deficient species. So if I look at this nitrogen, although it is carrying positive charge, let me tell you it has got 4 hydrogen connected to it. Meaning right now in the valence shell of this nitrogen atom, there are total 8 electrons. One bond corresponds to 2 electrons. So the octet of nitrogen atom is completed. Because of complete octet, such nitrogen would not want to accept electron anymore, which means it is not electrophilic at all. So although it is carrying positive charge, this will not belong to a category of cationic electrophile. Just like ammonium, you may have another example of hydronium ion, water upon protonation, where oxygen of that hydronium ion will be carrying positive charge but won't be electron deficient at all. Hence I said all the negatively charged species are always nucleophilic, but all positively charged species need not be electrophilic always. Alright guys, well, that was the basic introduction of reagents. Well, before we step into the further part of chapter, let me just brief you guys what we have seen so far. So my dear students, we started our discussion with the chapter of haloalkanes and haloarenes, where we saw haloalkanes and haloarenes are basically halogen substituted compounds which are alkanes or aromatic hydrocarbon. The only differentiating point between these two is in haloalkanes, halogen is connected to sp3 hybridized carbon atom, whereas in haloarenes, the halogen atom is connected to sp2 hybridized carbon atom. But to understand how exactly does this compound undergoes reactions, we'll have to first understand what are the two characteristics reaction these compounds undergo. So we studied haloalkanes, that is alkyl halides, shows its two characteristics reaction, that is nucleophilic substitution and elimination reactions. Hence, we decided to enter into nucleophilic substitution first. But before we actually learn the mechanisms, we have to understand the term called as reagent. Hence, we studied what are reagents. The species which attacks on the substrate is reagent. That reagent could be electron deficient, called electrophile, or could be electron rich, called as nucleophile, and these are their corresponding types. Now that we have learned this, we are all set to understand the solvents. Well guys, look, whenever you carry out any reaction between the two or more reactant, you use some medium for that reaction to carry out. So we saw one of the reactant is going to be our reagent. Since we are talking about nucleophilic substitution, nucleophile is going to be my reagent. Now since I am expecting this nucleophile to attack on substrate, how easily, how comfortably this nucleophile can attack on a substrate also depends upon what is the appropriate medium is used for that reaction to take place. Hence, it is very important first to understand the different types of solvent. Now since we have learned nucleophile and now we are going to learn a solvent, then we'll talk about the interaction between this nucleophile and solvent so that understanding of reaction mechanisms become easier. So everyone, let's talk about solvent first. Well, primarily we classify solvents into two categories, polar and non-polar. Don't read everything that you see on your screen. Let us understand stepwise first what are polar solvents. Let me take with the best example. Let's say water I have got. So that's how we represent water, where oxygen will be carrying two lone pair on it. Okay. Likewise, let me just take one more example, acetone, CH3, C double bond O and CH3. Okay guys, now what I want you all to look at is, well, acetone and water is very commonly used as a solvent. If you see here, oxygen and hydrogens are connected to each other via a covalent bond, in which oxygen being more electronegative, it will pull the bonding pair of electron toward itself, acquiring delta minus charge on O and leaving delta plus charge on hydrogen. The same thing will also take place from the other end as well. Due to electronegativity difference between the two covalently bonded atoms, there is a development of partial but opposite charges. Development of this partial and opposite charges is what you call it a generation of a dipole. A generation of dipole makes this bond a polar bond. Such a solvent having a polar bonds are known as polar solvents. So this is a polar solvent. Similarly, if you look at acetone, well, here as well carbon is connected to oxygen. Oxygen being more electronegative, it will carry delta minus and leaving delta plus charge on the carbon atom. So just like water, even acetone is a molecule where there is a development of polarization which makes even acetone as a polar solvent. However, one very interesting difference between these two kind of solvents that we can make out here is, in case of water, hydrogen is connected to more electronegative atom. Whenever hydrogen is connected to more electronegative atom, there is a possibility that this hydrogen can be lost in the form of H plus, of course under different circumstances. So such a polar solvent which is capable of furnishing H plus ion, furnishing meaning which is capable of donating H plus ion, we call such type of polar solvent as a protic polar solvent, or you can say polar protic solvent. I repeat, we know that there is a polarization of a bond here due to electronegativity difference, but this polarization is specifically between hydrogen and more electronegative atom like oxygen, could have been nitrogen, could have been fluorine, like that. So when hydrogen is connected to more electronegative atom, other than just a polarization, there is a possibility that this H can be lost as a H plus. H plus is a proton, meaning in other words, this molecule water is capable of furnishing or donating H plus ion, meaning it is capable of donating proton. Such polar solvents are known as polar protic solvents. Whereas here, there is just a polarization, but I don't see anywhere hydrogen connected to more electronegative atom. Here there is hydrogen, but it is connected to carbon. We want hydrogen to be connected to more electronegative atom like oxygen, nitrogen, fluorine. In that case, hydrogen can be lost in the form of proton. Then you can call it as protic. But here, there is just a polarization, but not capable of donating proton. So you call it as aprotic, polar aprotic solvent. Hence, we say polar solvents are of two types, polar protic, polar aprotic. The one which is capable of donating or furnishing proton, meaning H plus ion, are protic, and the one which cannot, you call them as aprotic. Well, now imagine if you have got a solvent where there is no polarization at all. For example, hexane. This is hexane here. Well guys, if I draw it in a very simple way, let's say if I write hexane in a very regular fashion that we do in organic chemistry, CH3, CH2, CH2, 4, 5 and 6, right? That's what you call it as N-hexane. In this N-hexane, you can see there are only two types of atoms connected. One is carbon-carbon, other is carbon and hydrogen. When we talk about carbon-carbon, both being identical atom, of course there is no differences in the electronegativity. And even if you consider carbon and hydrogen, the electronegativity difference between carbon and hydrogen is so negligibly small that we don't really consider that there is a polarization, like delta minus and delta plus in water or C double bond O. So here in case of hexane, because there is no bond containing two atoms differing in much of their electronegativity, there is no development of dipole. If there is no development of dipole, there is no polarity developed. Hence, such solvent belongs to a category of a non-polar solvents. So one way of finding out no polarity is when there is no differences in the electronegativity, like in hexane, like in case of benzene. Even in case of benzene, all the carbon atoms are sp2 hybridized because all are equal in their hybridized state. They all have identical electronegativities, hence there is no polarization. But sometimes you might see that the molecule may have a dipole, but more than one dipoles present, such that those dipoles cancel out each other. So the resultant dipole eventually becomes 0. For example, let me show you. We have got CCl4, or you can deal with CS2. To keep it simple, let me just show you CS2, carbon disulfide. Well, carbon disulfide structurally can be represented like this. That's how the structure of carbon disulfide is. It has a linear geometry, and of course S carrying 2 more lone pair on it. Now if you see here, carbon is connected to sulfur, which is more electronegative than carbon. Hence, sulfur being more electronegative, the representation of dipole will be from less electronegative atom towards more electronegative atom. So there is an individual dipole here. But at the same time, there is another dipole present in another C double bond S bond. So this dipole is exactly equal of that of this. So there are two dipoles which are equal in magnitude but opposite in direction. Being these two dipoles are present or directed in opposite direction, these dipoles cancel out each other's, and hence the resultant dipole mu r is considered to be 0, meaning resultant dipole is 0, meaning no pole meaning a molecule will be said to be non-polar. That's how everyone, a non-polar solvent could be either a molecule where there is no polarization developed because of no difference or negligible difference in the electronegativities of two bonded atoms, or maybe there are individual dipoles, but those individual dipoles cancel out each other so that the resultant dipole is 0. Even in case of CCl4, if you see, a carbon is connected to 4 chlorine which are oriented at the regular tetrahedron. So if you take the individual carbon chlorine bond, they are going to cancel out each other, so the resultant dipole will become 0. So everyone, that's how we classified the solvent into two categories, polar and non-polar. Polar solvents could be further of two types: polar protic, the one which are capable of donating H plus ion, and polar aprotic. Of course, we are going to see some more example of this, and then there comes is a non-polar solvent. Well, for us the important categories are polar solvents. So to learn some more example which we see often in the exams, in some of the question upon arrow they mentioned DMF, DMSO, we need to know what exactly they are. So let's have a look at examples of polar protic and polar aprotic solvent. So everyone, polar protic solvent, well, this is the most common type of solvents, and well, we have earlier studied about water. So due to electronegativity difference, we are certainly going to have delta minus and delta plus, which makes it polar. Hydrogen connected to more electronegative atom, which under circumstances may donate proton, so it is protic as well. Hence water is a polar protic solvent. Alcohol is another polar protic solvent, because again there is H and O. There will be development of dipole, and H connected to more electronegative atom makes it protic. Similarly, acetic acid, you can see polarization is not just between oxygen and hydrogen, it is also between carbon and oxygen. But due to its ability to donate H as H plus, it makes it protic. Hence I'll say these three are very common example of polar protic. Now everyone, important category that we have to learn is about polar aprotic, one of which I have already explained. I'll still write it again, once again. Acetone, well, structurally C double bond O and CH3. So electronegativity difference across carbon and oxygen will make it polar, but because there is no hydrogen connected to electronegative atom, it cannot donate proton, so it is aprotic. Next is DMSO. Let's say instead of carbon, if I take it sulfur, if I have got S double bond O, the only change I have made is instead of carbon I have taken sulfur, rest all I'm keeping as it is. So you call it dimethyl sulfoxide. Due to sulfur and oxygen differing in their electronegativities, O being more electronegative will acquire delta minus and sulfur will acquire delta plus, which makes it polar. but aprotic, because there is nowhere I can see hydrogen connected to more electronegative. Now guys, moving forward, little quickly, diethyl ether. Okay, diethyl ether. C2H5O. C2H5O. So due to carbon oxygen bond, there will be polarity, but no proton can be donated. So this is polar aprotic solvent. Another example is dimethyl formamide. Well, split this word first. Dimethyl, keep it aside. In formamide, it is amide of formic acid. Amide of formic acid. Okay, so formic acid is what? HCOOH. If I attach OH here, that's going to be formic acid. I'm making it amide, so it should be NH2. So that's formamide. Now one of the H I'm substituting by CH3. So this is now dimethyl formamide. Imagine instead of this 2-methyl, if I would have had HS, you would have called it as formamide. So in that case, it would have been protic, because hydrogen in that case would have been attached to nitrogen. So that H would have been protic. Now there is no hydrogen, I have got methyl. So the protic part have been removed, but polarity is still there across carbon and oxygen. So this is polar, but not capable of donating protons. So this is polar aprotic. Remember, hydrogen connected to doubly bonded carbon will not be able to donate it as H+. So this is not protic at all. So DMF, meaning dimethyl formamide, is a polar but aprotic solvent. And just like that, if I replace this H with CH3, the parent acid of this compound will be acetic acid. Hence, you call it as dimethyl acetamide. I'll write that structure. Replacing H with CH3. So we have got CH3 here, followed by C double bond O, N, and 2 of the H which would have been protic had it been here. I am replacing those with CH3. So this is what you call it as dimethyl acetamide. So guys, remember, several times you will see in a question upon arrow, they will mention some of the solvent in their abbreviation. If you see DMF, DMF is dimethyl formamide. If you see DMA, dimethyl acetamide, both of them are going to be polar but yet aprotic. Other than that, dimethyl ethyl ether or DMSO or even acetone, you will see several times would be used. So these all solvents belongs to category of polar but aprotic solvents. Alright everyone. Well everyone, so far we learned reagents. Again, in that important part of reagent which we have to learn is about nucleophile, because we are going to talk about nucleophilic substitution. We studied nucleophilic reagents, we studied solvent, and like I said, now we'll have to understand the interaction between these two. So if particular solvent is given to you, how strong the nucleophilic reagent would still be in that solvent, we'll have to understand that. So that's why we are proceeding further and learning solvent and its interaction with the nucleophile. So guys, let us consider case 1, that is nucleophilicity, meaning if the nucleophile is given, how well or how easily it can donate its lone pair, that is called nucleophilicity, in a polar protic solvent. Again, don't look at everything at once. Look at the simple reaction. Let's say I've got simple salt in a solid state. I took that in a water. Well, we know the fact water is polar protic solvent. Imagine if you take a salt, if you took a tablespoon of a salt in a glass of water, if you add it there and just stir it, you see that you get a transparent solution. That solution indicates that NaCl solid have been completely dissolved in a water. Because water is used as a solvent, this phenomena is also called as hydration of a salt. So the salt became hydrated is what we say. Meaning if I represent that hydrated salt in the form of chemical equation, we write it like this. NaX solid in water give you Na plus aqueous
X minus aqueous. This aqueous is very important, indicating that both the ions, cation and anion, have been solvated. Because solvent is water, you can say this cation and anion got hydrated. Right, everyone? The details of this you guys have learned way back in chemical bonding, where when this NaCl gets separated, some amount of energy is released, that is called as hydration energy. Then you compare lattice energy with hydration energy. If hydration energy is more than lattice energy, then compound is soluble, so on and so forth, right? But over there, when we discuss, we talk more about the cation. Here in organic chemistry, when we have to learn the impact of solvent on nucleophilicity, we have to understand the impact of water on a nucleophile. But we'll be discussing both once again. Let us talk about Na plus aqueous. Well guys, what does this Na plus aqueous means is, when you take NaCl solid in water, this water separate this Na plus and X minus, meaning the ionic bond which is present between Na plus and X minus have been broken with the help of new type of bond form using water, that is using hydration energy. So what happens actually when you write Na plus aqueous is, this Na plus ions get surrounded by several water molecules. So if you look at water, we know the fact, water being dipole, O being more electronegative, acquires bond pairs, so acquire delta minus, and hydrogen acquires delta plus. As a result of which, such solvent we call it as a polar solvent. Because it is polar, it attracts the positively charged ion, of course with the opposite pole. So if this is Na plus, the opposite pole of water will be what? Oxygen. So this Na plus ions will be attracted by the positively charged, the negatively charged atom, which is oxygen atom. That's how Na plus ion will be surrounded by a several water molecule through the negative pole, that is oxygen. See, what is that indicating? This is indicating that Na plus ion is forming a new bond with the oxygen atom. Because this is new bond, we all know the fact, formation of bond always stabilizes the species and releases the energy. So when this bond is formed, some amount of energy is released, which you call it as solvation energy. Because solvent uses water, you call it as hydration energy. So now because Na plus ions is surrounded by several water molecule, I will say Na plus ion is now hydrated. Hence you write it as Na plus aqueous. So I will say now Na plus ion is surrounded by water molecule by a force of attraction, that is Na plus, meaning this is ion, water is a dipole. So this kind of attraction or interaction is what you call it as ion dipole interaction. Hence I will say Na plus ions are solvated by ion dipole interaction. Keep this aside. For us, what is important is X minus, because that is nucleophile. So guys, X minus indicated is electron rich. So that electron rich species also being hydrated. Now how does that get hydrated? If this negatively charged species and if water is a dipole, then logically the positive pole of water will attract this negatively charged species. So the H carrying delta plus charge then attracts this negatively charged X minus. Again, when this bond is being formed, some amount of energy will be released. That energy release is what you call it as solvation energy, or because water is used as a solvent, you will call it as hydration energy. Now listen to me carefully. So here as well, X minus, meaning an ion, is solvated by a dipole. So even anion is solvated by what? Ion dipole interaction. But just imagine, if this X would have been fluoride ion, F minus. F is the smallest halide. Smaller the size of halide, more will be the electron density, because we know density is mass upon volume. If volume is smaller, the ratio will be higher, meaning density will be higher. So if X is F minus, then the density on F will be very high. So such electronegative atom carrying at least one lone pair, when comes in the vicinity of hydrogen atom, which itself connected to more electronegative atom, then the kind of force of attraction between such hydrogen and more electronegative atom carrying at least one lone pair is known as hydrogen bond. So if we take this F instead of general X, I will say this interaction would be a hydrogen bond. Meaning, guys, in other words, I can say hydrogen bonding, you can say, is an extreme case of ion dipole interaction, and that is valid only when you'll have the value of X as F. So if the value of X is F, you may term it as hydrogen bond, but in general this is nothing but the case of ion dipole interaction. All right, now let's think about a particular reaction. Imagine we have got substrate alkyl halide Rx, okay, and we are expecting a nucleophile. Okay, let's take nucleophile as X minus. Across carbon and halogen, X being more electronegative is going to acquire delta plus charge here, and this X minus wants to attack here. For this reaction to take place, let's say I have taken water as a solvent. Okay, now guys, we have got X minus as a nucleophile. We want to carry out a nucleophilic substitution at this alkyl halide, so that when this incoming X minus will attack here, this X will leave. Meaning we want this nucleophile to effectively act like a nucleophile and attack at the deficient center. But because this X minus is in presence of water, that X minus will be hydrated by a several water molecule via ion dipole interaction, which means this X minus is not free enough to attack at the deficient carbon. It is being caged, C-A-G-E-D, caged, or it is being captured by the several water molecule. Because it is captured by several water molecule, this X minus is not free enough to attack at the deficient carbon and carry out the nucleophilic substitution efficiently. Hence, the nucleophilicity of X minus is being suppressed because the solvent used is water. Can we say that? Because X minus is solvated by a water or hydrated by water, its nucleophilicity have been decreased or suppressed because it is being captured and not able to move freely to attack at the deficient carbon. So in general, we can say the impact of polar protic solvent on a nucleophilicity is the polar protic solvent captures the nucleophile and does not let it free enough to attack at the deficient carbon, so nucleophilicity is decreasing. Now let's consider if I have got different types of nucleophile. Different type meaning what? If I have got F minus, Cl minus, Br minus, and I minus. Guys, we all are aware that as we come down the group, size of atom increases, isn't it? Now, if I consider the value of X minus as F minus, because it is smaller in size, the density of electron on that small size atom will be very high. Higher the electron density, stronger will be the force of attraction between hydrogen and that anion. In case of F minus, we call it as hydrogen bond, which is the extreme case of ion dipole interaction. Meaning, if the size of anion is smaller, the hydrogen bond or ion dipole interaction will be stronger because more hydration energy will be released. So such F minus will be strongly captured by the solvent. Hence, its nucleophilicity will be least. Now imagine, if you come down the group from fluorine to chlorine to bromine to iodine, what happens to the size? Size of atom increases. If the size of this X minus is largest, let's say I minus, larger the size, meaning electron density on that iodine will be lesser, because we know the fact density is equal to mass upon volume, right? Everyone, I mean the general definition of density. So as the volume will increase, the ratio will decrease. If denominator will increase, the ratio will decrease, meaning density will decrease. Lesser the density on X minus, the force of attraction as a result of ion dipole interaction will be weaker, meaning larger size anion won't be that strongly captured as much as the F minus anion. So if larger size anion are not strongly captured by solvation, then such anion are relatively free enough to move in the solution and attack at the deficient carbon, meaning in other words its nucleophilicity will be better than those anion which are smaller in size, which means in another words, as you come down the group for such nucleophiles, size of nucleophile increases. So in polar protic solvents, its ability to act like a nucleophile or its nucleophilicity increases. Everyone, I repeat, as you come down the group, size of anion will increase. So larger size anion won't be strongly captured. Hence you can say they are relatively free. Hence the nucleophilic behavior will be better. Hence in a polar protic solvent, nucleophilicity increases down the group. Guys, conclusion is in polar protic solvent, the nucleophilicity increases down the group. Alright. Now let us think about, everyone, let us think about polar aprotic solvent. What are we going to talk about? Polar aprotic solvent. Well, so to understand, we have got NX, we are considering polar aprotic solvent, let's say DMSO. So we have got Na plus and DMSO will have delta minus and sulfur will have delta plus because oxygen is more electronegative. So such Na plus will be attracted by the negative pole, that is oxygen. So again this is ion dipole interaction. So the cation is being solvated by the solvent, whatever it is. But if I talk about X minus, guys, in the previous case we saw X minus was attracted by the polar protic solvent. Protic meaning hydrogen was connected to more electronegative atom and his hydrogen had a sufficient delta plus charge to attract the anion. Now when we are talking about polar aprotic, we won't have this hydrogen in aprotic solvent. If you don't have hydrogen in aprotic solvent, there is no one available to attract this anion. Meaning in polar aprotic solvent, due to absence of hydrogen connected to more electronegative atom, there will be no ion dipole interaction in polar aprotic solvent, and hence we say in polar aprotic solvent X minus ions are not solvated. Now tell me, if X minus ions are not solvated in polar aprotic solvent, then they are always free to attack. Then they are always free to attack, which means if I consider the similar reaction again here, that is Rx, X being more electronegative, carbon is acquiring delta plus, and we are expecting some nucleophile to attack at this deficient carbon, and we are carrying out reaction, let's say in presence of aprotic solvent DMSO. We know the fact this DMSO is not going to solvate nucleophile because polar aprotic solvent cannot solvate anion because they do not have hydrogen to attract that negatively charged ion. Meaning nucleophiles are always free. If these nucleophiles are always free, then whichever nucleophile is more electron dense, will be a better nucleophile to attack at the deficient carbon. Yes, logically. What is definition? Nucleophiles are electron rich species which has a tendency to attack at the deficient center. So more electron rich the species, faster it can attack at the deficient center. So more electron rich species meaning what? The one which is more electron dense. Hence, if I compare several nucleophiles, let's say halide ions, F minus, Cl minus, Br minus and I minus. For them, as we come down the group, what happens to the size? Size increases. As size increases, what happens to density? As the size will increase, if the denominator will increase, the density will decrease. Meaning, can I say F is the most dense than Cl minus, than Br minus, than I minus. More dense the nucleophile is, better nucleophilic it is. Hence, the rate of nucleophilic substitution will be faster if the solvent is polar aprotic. Guys, I repeat one more time. In case of polar aprotic solvent, anions are not solvated due to absence of hydrogen atom. If they are not solvated, meaning all of them are free. So if all are free, all can attack at the deficient carbon. But of course, if I relatively compare the reactivity, then one which is more electron dense will be better nucleophile, can attack at the deficient carbon faster. More dense meaning as you come down the group, size of halogen increases, meaning density decreases. So the small size halogen or halide ion will be a better nucleophile. Hence, in polar aprotic solvent, the nucleophilicity down the group decreases. So these two are exactly the opposite impacts of the solvent. In case of polar protic solvent, large size anion will be relatively less captured, hence better nucleophile. So in polar protic solvent, down the group nucleophilicity increases. But in polar aprotic solvent, small size nucleophiles are more dense and hence better nucleophile. So down the group size increases, meaning nucleophilicity decreases. So just to add a point here, down the group size increases, nucleophilicity decreases. What is it? Polar aprotic solvent. But in polar protic solvent, down the group size increases, anion become less captured and hence nucleophilicity increases. Alright guys, don't worry, we are going to collectively summarize these points again in the next slide, but just as we are discussing, I'm writing down some important points. Now question arises, what if I'm comparing nucleophilicity across the period? Well guys, if you see, the nucleophilicity is getting affected by this solvent, polar protic and polar aprotic, because there is enormous difference in the size down the group. In the modern periodic table, the trend in the size that we have learnt is, as we come down the group, the size increases because the next electron is added in the new shell altogether. And if the size is differing too much, then there is going to be impact of a solvent on those kind of nucleophile. Now we are talking about, what if we have got nucleophiles across a period? What if we have got nucleophile across the period? Like if I've got CH3 minus, NH2 minus, OH minus and F minus. These all are the anions, and all anions are negatively charged species, meaning they are nucleophilic. So if we have got nucleophile across the period, then does this solvent affect the nucleophilicity? Well, let me tell you. Across the period, although moving from left to right, size decreases, but the decrement in the size is negligible. So because decrement in the size is negligible, you can say the size of those anions, more or less it is going to remain same. If there is not much of a difference of the sizes, solvent cannot have enough impact on their nucleophilicity. Hence guys, if we have several nucleophile across the period, then solvent will have no impact on their nucleophilicity. Then obvious question arises, then how do we find out the nucleophilic order when the species are of the same period? Well, I will tell you. Look, let's say if I've got nucleophiles across a period, I'll just write it down over here, okay? I've got CH3 minus, NH2 minus, OH minus with 3 lone pair on O, and F minus with 4 lone pair on O. Okay, guys, let's think about what you have learned in modern periodic table. When you're coming down the group, size is increasing. Size is inversely related to electronegativity, meaning electronegativity is decreasing. But decrement in the electronegativity, and when compared with the increase in the size, size is always a dominant factor. So down the group, size is a dominant factor, not electronegativity. As you move from left to right across the period, although there is decrement in the size, but it is negligible. So size is not the dominant factor, but electronegativity is the dominant factor. So as you move from left to right, electronegativity increases. That's why When you are comparing the nucleophilicity down the group, we are considering size as the factor. But when I'm going to compare nucleophiles across the period, I will be considering electronegativity as the dominant factor. So as you move from left to right, you see electronegativity of atom is increasing. More electronegative the atom is, more strongly it will hold the electron density. And this negative charge due to extra electron will be held tightly by this F because it is more electronegative, which means it will not be easily able to donate the electron density. And ability to donate electron density is the Lewis basic nature, and it is also the nucleophilic nature. What is nucleophilicity? Ability of an atom to donate its electron density to the deficient carbon is the nucleophilicity. So more electronegative the atom is, more tightly it will hold the electron density, hence its ability to donate electron pair, meaning its nucleophilicity will decrease. Hence we say, as you move from left to right across the period, I'll write it down. As you move from left to right across the period, left to right, electronegativity increases. If electronegativity increases, ability to hold electron density will increase, meaning donation tendency will decrease, meaning Lewis basic character will decrease, meaning in other words, nucleophilicity will also decrease. Hence your correct order would be F minus will be least nucleophilic because it is most electronegative, then OH minus better nucleophile, then NH2 minus, and the best nucleophile will be methyl carbanion. So guys, this is something that you have to understand when you are comparing nucleophilicity across the period. So everyone, so far what we have learned: impact of solvent on nucleophilicity. Again, quickly everyone, polar protic solvent captures the anion by ion dipole interaction. If it is F minus, you may consider it to be hydrogen bonding. Strongly the anions are captured, less its ability to act like a nucleophile. So small size anion are captured strongly in polar protic. As you come down the group, size increases. Due to larger size, anions are not that strongly captured, so they are relatively free, hence nucleophilicity increases. So in polar protic, down the group, nucleophilicity increases. In polar aprotic solvent, the nucleophiles are not solvated at all. If they are not solvated at all, then whichever is more dense will be the best nucleophile. More dense meaning small size atom. So as you come down the group, size increases, nucleophilicity decreases in polar aprotic. The impact of solvent will no more exist if the nucleophiles are across the period because difference in the size is negligible. So what comes into picture is electronegativity. As you move from left to right, electronegativity increases, Lewis basic nature decreases, and the nucleophilicity also decreases. Hence methyl carbanion is best nucleophile, whereas fluoride is the poorest among these four stated nucleophiles. Well, so here are some important points that I just discussed. I put them on the screen for you guys to refer it anytime you want. So you can see nucleophiles being captured, cage, it is not free to move in the solution, hence in general nucleophilicity decreases. Strength of hydrogen bond. Well, I'll again mention hydrogen bond will come into picture when it is F minus, otherwise you can see strength of ion dipole interaction. Ion dipole interaction. Strength of ion dipole interaction depends upon how dense the halide is. That is, hydrogen bond is stronger when the small size halide exists. So moving down the group from F to Cl to Br to I, size increases. Strength of hydrogen bond, again whenever you see hydrogen bond, I want you to think of ion dipole interaction decreases. Hence down the group X minus are less captured, meaning relatively free. Hence nucleophilicity increases down the group in polar protic, like I mentioned earlier. Since in polar aprotic solvent does not contain H attached to electronegative atom, hence cannot solvate the anion. Thus anions remains non-solvated. If they are non-solvated, then small size anion So in polar aprotic solvents, nucleophiles are free, which are not caged, which means the halide ion with more electron density is more nucleophilic. Hence, down the group, F will be the best nucleophile. Size increases, meaning density decreases. That is, nucleophilicity decreases. And like I mentioned, solvent has no impact on nucleophilic order for the nucleophile from the same period. That is CH3 minus up to F minus, what we discussed. Alright guys, well, other than this, there are some important characteristics which I want you all to always remember. So we are starting with characteristics of nucleophile. Other than these three results, polar protic down the group, polar aprotic down the group, these are two results. We also discuss nucleophile across the period. Other than these three, there are some more characteristics which I want you all to always focus on, which is right here. Well, anionic nucleophiles are stronger than its corresponding neutral nucleophile. Well guys, isn't it logical? Suppose if I say I have got example, let's say I have got OH minus, and if I take its conjugate acid, that is water. So from water, if you remove H plus ion, you get the conjugate base, that is OH minus. That clearly indicates oxygen is more electron rich in case of OH minus ion than just oxygen of water. Being more electron rich, it will be more nucleophilic. So OH minus ions are stronger nucleophile than water. So anionic nucleophiles are stronger than its corresponding neutral compound. That's what the point is saying. Other than this, let me take another example. Let's say if we have got alkoxide ion, comparing that with alcohol. So alkoxide is obtained by loss of proton from alcohol. So this is the conjugate base of alcohol. Being conjugate base, it is more nucleophilic. Similarly, ammonia is NH3. I am taking its conjugate base, that is NH2 minus. Comparing that with NH3. This is anionic, so more nucleophilic, etc. So everyone, conjugate base, or you can say anionic nucleophiles, are always stronger nucleophile than its corresponding neutral or conjugate acid. That's the fourth point in the nucleophilicity. Well, across the period, this is what we have discussed already. We are just putting it again. Across the period, nucleophilicity is parallel to basicity. Right? Just now we saw, if we have got CH3 minus, this is what we have discussed, okay? If you compare that with amide, with hydroxide and fluoride. So as we move from left to right, well, as we move from left to right, electronegativity increases from carbon to nitrogen to oxygen to fluorine. Electronegativity increases, meaning ability to hold electron density is more, meaning to donate electron density tendency decreases. So basic nature will decrease. So F, being most electronegative, will be least interested in donating. If donation ability decreases, meaning nucleophilic nature also decreases. Guys, this is what we have discussed just now. So that's going to be the nucleophilic order across the period. So 4 points overall. Now let us consider if the negative charge, meaning if the nucleophilicity is residing on the same atom, all are oxygen, let's say, then what happens to the nucleophilicity? Let us understand that. So listen, whenever you see negative charge is residing on the same atom, so you have got several molecules where negative charge on the same atom, like OH minus, negative charge is on O, alkoxide ion, negative charge is on O, phenate ion, phenol's conjugate base, negative charge is on O, or carboxylate ion, RCO minus. Whenever you see negative charge is residing on the same atom, then nucleophilicity is parallel to its basicity. Whenever negative charge is on the same atom, nucleophilic order is parallel to its basic order. What does that mean? Look, now we have got examples where I've got RCOO minus, conjugate base of carboxylic acid, PHO minus conjugate base of phenol, OH minus ion conjugate base of water, and ETO minus conjugate base of ethanol. And we have to compare the nucleophilic order of this four. Now when I compare all these four species, I can clearly see that the negative charge is residing on the same atom. That's what we are talking here. When the negative charge is residing on the same atom, nucleophilic order is same as that of the basic order. Meaning whichever is a stronger base will be a stronger nucleophile. Now what they've given is a conjugate base. To check the order of conjugate base, I'll have to check the order of its acidic nature. Meaning I'll have to convert all of them into their conjugate acid and check their order of acidic strength. Why? Because I know the fact stronger acid has poor conjugate base. I'll just write it down for you. Stronger acid conjugate base is poor. So let's see if we have got stronger acids conjugate base is poor. Stronger acids conjugate base is poor. So what I'm doing, I'm converting all of them into their conjugate acids. What I'm doing is I'm converting all of them into their conjugate acids. How do you get conjugate acid? Simply add proton here. So this will be CH3 C double bond OOH. Then we have got PHO minus, meaning it is PH OH. OH minus, add what H plus over there, so that's going to be H2O. Add H here, so that's going to be ETOH. Alright, so we have got acetic acid, phenol, water, and ethanol. And now if someone asks me, write down the order of acidic strength, I will say carboxylic acid is strongest acid, then phenol, then water, and then ethanol. We know the fact only methyl alcohol is stronger than water, rest all alcohol are weaker acid than water. So what you have mentioned just now is the order of acidic strength. Okay, so what we have said, stronger acids conjugate bases are poor. So if this is the strongest acid, its conjugate base, that is acetic acid, is going to be poorest base. Strongest acid conjugate base is poor. So acetate is poorest base. Then phenate is poor base. OH minus is relatively stronger base, and ethoxide ion is the strongest base. And now once you know that this is the order of basic strength, order of basic strength, then dear students, please read what we have mentioned earlier. When the negative charge on the same atom, nucleophilic order is parallel to basic order, meaning whatever is a basic order here, same is going to be the nucleophilic order. So order of basic strength and also equal to order of nucleophilicity. So what you see here as the order itself is the order of nucleophilicity. So ethoxide ion, which was poorest conjugate base, will which was the strongest conjugate base, is going to be the strongest nucleophile here. So whenever they ask you any question related to order of nucleophilicity, simply check whether those nucleophiles are from a particular group or from a particular period, and if you see the negative charge on the same atom, then you all know that the nucleophilic order will be same as the basic order. However, there might be point of confusion when you will see the negative charge on the same atom, but there is steric hindrance operating in these molecules. Like over here, if you ideally see negative charge on the same atom, but they all are from the different functional group. This is from acid, this is from phenol, this is from water, this is from ethanol. If I give you some example like this, tertiary butoxide, isopropoxide, ethoxide and methoxide. So see, here also the negative charge is residing on the same atom, but there is difference in the steric hindrance. Here the negative charge was on the same atom, but they all were from the different functional group. Here negative charge on the same atom, but all are from the alcohol only. This is conjugate base of tertiary butyl alcohol. This is conjugate base of isopropyl alcohol. This is conjugate base of ethanol, and this is of that of methanol. So you can see here it is bulky alkyl group present. This is relatively smaller. This is the smaller, and this is the smallest alkyl group present. Meaning as you move from methoxide to third butoxide, bulkiness of alkyl group is increasing. So I will say steric hindrance is increasing. Hence, listen to this. When a negative charge is on the same atom, but the steric hindrance is operated, then basic order remains same, but the nucleophilic order reverses. When the negative charge is on the same atom, but the steric hindrance is operated in the molecule, then the basic order remains as it is. As it is as in, you check the order of corresponding acid, meaning conjugate acid, and stronger acid conjugate base is poor. So you'll find out the basic order according to the thumb rule that we have studied in the previous slide. But the nucleophilic order will reverse. So tertiary butoxide is the strongest base and methoxide is the weakest base. This is the basic order. You can check with the logic that we have applied. So if this is weakest base, if this is the weakest base, then it is going to be the strongest nucleophile. Because whatever is the basic order, the nucleophilic order is going to be reverse. Hence methoxide is strongest nucleophile, then ethoxide, then isopropoxide, and then third butoxide is the weakest nucleophile. To understand this, I am telling you one more logical thing, probably that helps you to remember. Guys, try to recall what nucleophile does. Nucleophiles attacks at the deficient carbon. Nucleophile attacks at the deficient carbon of alkyl group, right? In other words, the nucleophile with its lone pair carrying orbital overlaps with the orbital of the carbon which is a deficient carbon, right? For that overlapping to take place, the nucleophile carrying lone pairing orbital should be sufficiently close enough to the carbon which is deficient. For that sufficient closeness to take place, the nucleophile should be small in size. Imagine if nucleophile is bulkier in size, it won't be able to approach the deficient carbon's orbital for the overlapping. Hence, that will create problem in formation of a bond between nucleophile and the deficient carbon. Hence, you can remember it this way. Small size nucleophile will be able to attack the deficient carbon better because of its smaller size. It can penetrate well in the molecule to carry out effective overlap. But the larger size of nucleophile won't be able to reach closer to the deficient carbon orbital to carry out the nucleophilic reaction. So guys, in short, when you see negative charge on the same atom, and if those negatively charged species are from the different functional group, then in that case the basic order and the nucleophilic order remains same. If you see the negative charge on the same atom but they are from the same functional group, and if the steric hindrance is operated, the smaller size nucleophile is going to be the best nucleophile. To conclude this all, let me tell you important point that we discussed. First, effect of polar protic and aprotic. In polar protic solvent, down the group nucleophilicity increases. In polar aprotic solvent, down the group nucleophilicity decreases. Across the period, nucleophilic order is not affected by the solvent but affected by the electronegativity. As you move from left to right, electronegativity increases, nucleophilicity decreases. Anionic species, number 4. Anionic species will always be a better nucleophile than its conjugate acid. Like OH minus better nucleophile than that of water, so on and so forth. And then if negative charge is on the same atom, then the nucleophilic order is same as that of basic order. Another simple trick to remember, if you see negative charge on the same atom but they are of the different functional group. Fifth point, if the negative charge is on the same atom, if the negative charge is on the 6 point, I'm sorry. If negative charge is on the same atom and if the steric hindrance is operated, then basic order remains as it is, but the nucleophilic order reverses. Meaning the larger size nucleophile will be the weakest nucleophile and the smaller size will be the best nucleophile. That happens in case of nucleophile, where they all are from the same functional group like alcohol. Guys, that was all about nucleophile and its important characteristics. So I want you guys to quickly have a look at this question and solve it immediately. Well, read this. It's a very simple question. I just wanted to see how attentive you guys are. All right, I'll just drink water till then. Okay, everyone. Across the period from left to right, what happens to the nucleophilicity? Well, what we have learned so far, as you move from left to right, electronegativity increases. So Lewis basic character decreases because lone pair can be held tightly, and hence its nucleophilicity also decreases. So as you move from left to right across a period, nucleophilicity decreases. That's your correct choice. I think it was pretty simple. Everyone could do it, right? Lovely, guys. Now the last part that probably we would be looking forward to learn is about the leaving group. Keeping an eye on the time limitations of this session, guys, I would like to cover this one, a small subtopic here, that is about the leaving group. Well, what exactly are the leaving groups? Well, guys, we talked about substitution and elimination reactions, right? So let me show you the general representation once again here. Look, what we studied is, if we have, let's say this is our substrate, and this is your leaving group L, and we have got hydrogen. We saw alkyl halide shows two characteristics reaction. One is elimination, other is substitution. Elimination is found to be taking place in presence of base. Substitution is found to be taking place in presence of nucleophile. Base is any electron rich species which has a tendency to accept proton. Nucleophile is that electron rich species which attacks a deficient center, which is carbon. So what base does? Base abstract the hydrogen atom. As soon as hydrogen atom is lost as H plus, sigma bond shifts here, and now see, carbon and leaving group bond is broken, so the L is lost in the form of L minus, and along with this you will get double bond between the two carbon, so it results in the formation of alkene. Right, everyone? Similarly, if we have got a nucleophile, nucleophile is that electron rich species which attacks at the deficient carbon. So let's assume carbon and the first atom of leaving group is more electronegative than carbon, and this carbon is going to acquire delta plus charge. So nucleophile by definition will attack at the deficient carbon and the leaving group will leave. So here as well, the leaving group is leaving in the form of L minus. However, the product obtained won't be unsaturated. It's going to be a saturated product here. The only difference you'll see, instead of L, you'll have a nucleophile. So rest of the structure as it is. Hydrogen is still intact. And here we have got nucleophile. Okay, everyone? Well, what I want you to look at is whether it is substitution reaction or whether it is elimination reaction. Other than the product, one common thing that we have observed is the departure of a leaving group. So when base or a nucleophile carry out reaction of alkyl halide, the species that leaves from the substrate, generally in the form of anion, sometimes it could be in the form of a neutral molecule like water as well, Generally in the form of anion is what you call it as the leaving group, sometimes also called as nucleophiles. Generally we symbolize it as L group. So read it here. In a nucleophilic substitution and elimination reactions, when nucleophile or base attacks the substrate, an ion or a neutral atom or a group of atom departs from the substrate, generally in the form of anion is what you call it as a leaving group. Okay. So what we learned here is leaving group is the one which is generally in the form of anion. Now I want you guys to look at it in a very logical manner. Tell me, if the leaving group which has left is not stable, let's say, generally acid base reaction you will see takes place in an equilibrium. So if the leaving group which is obtained in the form of anion is not stable, then your reaction will be driven in a backward direction, right? So if reaction has to be driven in the forward direction, which means the leaving group even after its departure must be stable. So the better leaving group is going to be the one which is stable even after its departure. So now we are talking about the good leaving group. Who's a good leaving group? The one who is stable even after its departure. Because if it is not stable, the reaction might not take place in the forward direction. So good leaving group is the one which is a stable anion. I'll just write it down here. We are talking about a good leaving group. What we have learned so far is good leaving group is the one which is stable anion. Right, everyone? Stable anion, meaning in other words, can I say a stable conjugate base? Okay, think in this way. An acid, when donate H plus ion, you get an anion which you call it as conjugate base. An acid, when donate H plus ion, you get an anion which is a conjugate base. So anion is nothing but a conjugate base as well. But we want that anion to be stable, meaning we want stable conjugate base. So stable anion is nothing but a stable conjugate base. Stable anion, everyone, is nothing but a stable conjugate base. Well, we also know the fact a stable conjugate base you always get from a strong acid. So stable conjugate base will be obtained from a strong acid. Guys, not to forget, stable conjugate base will be a conjugate base of stronger acid. So it's a conjugate base of strong acid. And guys, if acid is stronger, then its conjugate base is always what? Weaker, isn't it? If acid is stronger, its conjugate base is weaker. Just now we saw when we were thinking about the order of basic strength in the nucleophilic order. Stronger acids conjugate base is weaker, weaker acids conjugate base is stronger. Right now we are talking about what? Conjugate base of strong acids. So conjugate base of strong acid is always what? A weaker or a poor conjugate base. So strong acids conjugate base is poor, or you can say weaker conjugate base, which means poor conjugate base is a good leaving group. A poor conjugate base is a good leaving group. So guys, in short, I will say, what is a good leaving group? Poor bases are good leaving group. I repeat, good leaving group are the one which are obtained as a stable anion. Stable anion, anions are generally conjugate base. So stable anion meaning stable conjugate base. Stable conjugate base you always get from a strong acid. So stable anion meaning a conjugate base of strong acid. Strong acids conjugate bases are always poor conjugate base. Meaning, in other words, poor bases are a good leaving group. So I'll write down an important statement. Remember, poor bases are good leaving group. Poor bases are good leaving group. All right, guys, I want you all to remember this. It is an important statement because using this simple statement, we will also be able to find out the leaving group ability. So if someone asks us, find out the order of leaving group ability, what will you do? You'll convert all of those leaving group into its conjugate acid. You'll take the order of acidic strength. Strong acids conjugate base is poor, and that poor base is always going to be a good leaving group. So guys, poor bases are good leaving group is what we have derived from this. And now, other than your normal halide as a leaving group, there are some more examples of leaving group that we in general study in organic chemistry. So I want you guys to get introduced to those as well. So here is the list of some of the important very good leaving group, such as triplet tosylate. This is an important one. Brosylate and mesylate. Well, you can see here R is the alkyl group connected to OSO2CF3. So this part is known as triplet connected to alkyl, so we call it as alkyl triplet. Imagine if I allow this to react with some nucleophile. So because this is good leaving group, nucleophile will attack and immediately this molecule as a triplet and will leave. So this triplet is symbolized as OTF. You see that OTF. If I attach R here, so that will be alkyl triplet, which is this structure. So alkyl triplet is one of the good leaving group. Now replace this CF3 by a toluene group, that is benzene carrying CH3 at the para position. So because we are putting toluene here, now this is called as tosylate. So this is an important structure. Remember, tosylate. So alkyl tosylate is another commonly used a leaving group. You will see later in the chapter of alcohol we come across reaction called as tosylation. That is, alcoholic OH will be converted to a tosylate group, so that the OH, which alone is not a good leaving group, it can be made as a good leaving group. So that's tosylate. Then we have got brosylate, symbolized as OBS. So you had CF3, you replace this CF3 with toluene group. Now instead of CH2 you have got Br, so that's what you call it as brosylate. So that's your alkyl brosylate. And if I replace instead of CH2, if I just make it CH3, so this is methyl, so you call it as mesylate. So everyone, other than normal halide, hydroxide, alkoxide and carboxylate, these are some of the, you can say, off track leaving group that you might see in the reaction. So the moment you see that alkyl group is connected to any of this, that indicate they are good leaving group, and good leaving group always enhances the rate of nucleophilic substitution. As we will enter into nucleophilic substitution reaction, you will learn all the important details of how leaving groups are important to carry out this reaction. As of now, guys, let me summarize what we have seen in this today's lecture number 1 of Haloalkanes and Haloarenes. To begin with, we saw that how understanding of reaction mechanism is important, but to understand the reaction mechanism, at the same time we need to understand such simple term like what are nucleophilic reagent, then we need to understand the different types of solvent, then we need to understand the impact of solvent on nucleophilicity, and then at the end the leaving groups. So all small subtopics, we have studied them in very detail. I want you guys to keep on revising them and keep shining. Guys, we'll stop here and I'll see you soon in the next class with the actual reaction mechanism. Will start with unimolecular nucleophilic substitution. I'll see you soon. Thank you so much, everyone.